Recording. We are live. Audio and video is up. Welcome to Structural Analysis this Friday. And wait, what is that? What is that on the slide that says no homework for the weekend? Can you believe that? Who is this guy? Who is Dr. Mike? Where is he? Where is Dr. Mike and who is this new professor? Now, I'm going to hold off on assigning the next homework assignment. And the reason why is because of what we're talking about today. I kind of want today's lecture to sort of seep in a little bit because I want to spend Monday on our last deflection topic talking about frames. And I want to sort of knock frames out really quickly. And what we discuss with frames, I want to feel natural. And I also want you to maybe take a look at the homework assignment that you just did and see if there are ways that you could make it easier. If I was a betting man and I saw your homework assignments, I'm imagining that there was maybe a little bit of this going on. From some of you, the whole, everything in class was easy, and we get the homework assignment, and it's like, good Lord, the math, the horror, the algebra, and what I want to do today is I kind of did that on purpose because I want today's lecture, I wanted you to be sort of receptive to some different ways of going about integration. And for some of you who are saying, like, if I got this one wrong, one of the reasons that I'm not doing a new assignment this weekend is I'm going to tell my TA to hold off on grading it. And if you want to take another look at the homework assignment, I'm going to give you the freedom to do that over the weekend. So if you, and maybe some of the things that we talk about today, you might look at the homework assignment a little differently and go, maybe it wasn't as bad if I had tried some of these tips and tricks. The point was I wanted you to be receptive to, like, I wanted you to go through like the hardest way possible of doing it so that today, some of the tips and tricks make your life a little easier. Now, I'm going to go ahead and tell you today, there is going to be a lot of math, but there aren't any in-class examples. I just want to talk about strategy and talk about the process. Now, I do have one announcement that I need to mention now, and that's RISA. Okay, so RISA stands for Rapid Interactive Structural Analysis. You are quite welcome. RISA stands for Rapid Interactive Structural Analysis, and it is the software program that I want to show you on starting next week. So, structural engineers in practice, you do structural analysis using software programs, and there's oodles of them out there. I tend to like RISA because RISA is easy. In my opinion, it's one of the easiest programs to learn. The learning curve is not steep at all. And also, if you learn how to use RISA, you can pick up other programs. What we're going to do is since we're doing this at a distance, first off, I don't make structural analysis very heavy on the software. So we're actually just going to use the demo in here. We're going to be fine. If you go to Blackboard, there's a link to install the demo. If you could install the demo by Wednesday on your computers, that would be great because we're going to start using RISA in class. And I'm going to do some sort of chewing on my end on how to do this via online because I understand that some of you are going to be watching the lecture, on your computer and then using the program on your computer, right? So I know that there might be a lot of flipping back and forth, and so I'm going to chew on how to make that as smooth as possible. So one thing I'll mention on Wednesday and on Friday is that if you have maybe a mobile device or a tablet or something like that, it might be a good idea to try and access the class via your mobile device so that you could use RISA on your laptop. And I'm just throwing that out there as a suggestion. I'm going to try and build the lectures so that the flipping back and forth, I'm going to try and reduce that as much as possible. And we're only going to do RISA for 2 days, so that's not going to be so bad. But like I said, but just make sure you have RISA installed by Wednesday. and so we could get rocking and rolling on that. Where is it located on Blackboard? If you go to, that's a great question. If you go to the lecture notes section, so you know how we had like topic 3 was, topic 4 was, and you could do that. You could use split screen, laptop and TV. That's fine too if you have an HDMI cord. Just be prepared Wednesday and Friday. If you go to the lecture notes, so like topic 3 is trusses, topic 4 is shear and moment diagrams, topic 5 is deflections. There's a new thing there called topic 6, and it says structural analysis using RISA, and there's a link that you can click that'll show you how to download it and register. As I said, as long as you get that installed by Wednesday, you're good. Great. Okay, so let's talk about virtual work. Now, here's the thing, and I said this sort of in passing on Wednesday, but I kind of want to emphasize this. I could stop talking about deflections right now. Everybody in this class has the tools and the capability to do any beam deflection problem just using this process. You know, you need your real moment functions, you need your virtual moment functions, you need the modulus of elasticity, the moment of inertia, and you just sum up all your integrals. But as you found probably on this last homework assignment, is that that's easier said than done, Dr. Mike, because, you know, yeah, I get the theory, but what ends up happening is, you know, you end up having ridiculous amounts of calculus, ridiculous amounts of algebra, depending upon how you go about it. And what I want to show you is that there are some ways to make this process a lot. And I know that this type of stuff is discussed in various textbooks, but what I've done is compiled, like, you know, I've been teaching this class for a long time, and I've you know, I can't tell you how many homeworks I've graded, I can't tell you how many problems I've done, and these are sort of my 4 tips and tricks that can help you when computing beam deflections. Okay, and first off, I'm going to summarize them right now. And I promise you, by doing this, you're going to make your life easier when doing a homework problem, or doing an exam problem, or doing just a structural analysis problem. The first is to exploit symmetry whenever possible. And that right off the bat is something I would say, not just about deflections, but about structural analysis in general. And really, like, mathematics and physics tends to be easier on the analyst when they're able to exploit symmetry. Symmetry, and as Mr. Blizzard said, that symmetry is such a good friend to have. He's absolutely right, that if you can exploit symmetry, the math will be easier, guaranteed. Now, and I really emphasize that because a lot of times in real life structural engineering applications, we can do that. You know, I'm here in my office. Above my office, there are beams supporting the floor above. And those beams are defined as simply supported beams with uniform distributed loads. Those are symmetric structures. And so explaining symmetry makes life a lot easier during the analysis and design phase. Now, here, that I think is pretty obvious. The other 3 maybe aren't so obvious, and I'm going to go ahead and just spell them out. Number 2, use a coordinate system at the free end when possible, and this particularly applies to cantilevered beams and to overhanging beams, is that try and define a coordinate system at the free end of the beam as opposed to the fixed end of the beam. Okay, that's point 2. Point 3, when cutting a section, always look toward the origin. And up until now, I have crafted my example problems in sort of a way that I was doing that and it seemed obvious. Well, when you're defining your own coordinate systems and doing your own problems, it may not seem so obvious, and I want to show you why you want to look towards the origin. And number 4, this is probably one that you may not find spelled out in a lot of textbooks, but exploit integrals with a lower bound of 0. And that'll become clear here in a little bit. There's a number of different ways of saying number 4. Basically, number 4 revolves around using 2 coordinate systems, but there's a reason why, and what is said in number 4, that is why you would use 2 coordinate systems. But let's take each of these one at a time. And I'm going to take it slow, and I really want you all in chat that if you've got questions, if you've got if you want to relate this to the homework or something, like, please, like, I don't even have any in-class examples today. This is just like a discussion, and really so that you can understand the procedure. So let's talk about the first point. And the first point was to exploit symmetry. Okay. Now I want to look at this beam. We looked at this beam like at the very, very, very tail end of class on Wednesday. We really didn't give this beam enough time to respect what was going on. Now let's digest it a bit. I have a beam that is simply supported it's symmetric. Now we're going to talk about exactly what I mean by symmetric. And it has a point load at midspan. And what I want to do in this problem is determine the deflection at C. Now, first point I want to mention before we move past all this is I told you all a long time ago that I try and ground what I do in this class in reality. And so one question you might have is, oh, come on, Dr. Mike, do people really build beams like that? Yes, people do. A very, very common place that you see beams like that is in bridges. For instance, when you have a steel plate girder, so a plate girder is an I-beam that's fabricated from a series of plates. So you actually pick your top flange, pick your web, pick your bottom flange, and actually weld it together. And you do that when you have really, really long bridges because you want to tailor the girder to the specific, shear demand and the load demand and the moment demand and so on and so forth. Well, if you look at the moment diagram for a simply supported beam, the bending moments tend to be the biggest at midspan. And so what you'll find is that the plates, the flanges and the webs, they'll actually be thicker in the middle at midspan than they will be near the supports. And so what you see here is a very real thing that the structural engineers would deal with. Well, using the tools that we had developed up until Wednesday, you'd need 4 integrals to do this problem because you'd have to integrate from 0 to 10 and then from 10 to midspan and from midspan to 34 and then from 34 to the end. And the reason you'd have to do that is because the real and virtual moment functions, you've got 2 each, one from 0 to midspan and one from midspan to the end. And then you've got this separation of this change in your moment of inertia. So you got 4 different integrals that you got to chug out. And it's like, oh my Lord, like this is ridiculous. Like take a look at some of those last integrals. You're having to take 176 minus 4x times 22 minus x over 2. So not only do you have all this ridiculous amount of math, but you've got foiling to do. It's like, come on, Dr. Mike, there's got to be a way of making this easier. The answer is to exploit symmetry. Okay, so first off, we're doing integrals. Okay, so let's go back to basic math. Let's go back to integrals. How can symmetry help? So I got a really simple example here. Let's consider the function f of x is 6x minus x squared. And I'm going to stop the share here because I want to use the board here. I picked this function because it's representative of a lot of moment diagrams that we see. It's a parabola that's downward, and it's got really clear intersection points. So this is x, this is y, okay? And so it's a parabola, and it looks something like this, okay? So that's kind of what the parabola looks like. And so it's 6x minus x squared, and you could figure out where these intersection points are pretty easily. This is x equals 0, and this is x equals 6. Well, if I wanted to determine the area under curve, one way of determining that would just be that the area is the integral of 6x minus x squared from 0 to 6, okay? And if you do that, if you chug that out, I think the answer you end up getting is 36, okay? And that's the total area under the curve. That's one way of doing it. Another way of doing it is to say, you know what, I'm only going to integrate half of it. I'm going to integrate this part right here. Integrate from 0 to 3. And then I'm going to multiply the whole thing by 2. And when I do that, I end up getting 36 as well, okay? Now, from a calculus standpoint, there's really there's no difference, and there's probably no reason to do this if all we were doing was just an integral from Math 229. So why do that here? Why bring that up? Well, the reason is the physics, okay? This beam, if we go back to this beam is symmetric. And in order to exploit symmetry, I want to be clear, you have to have 4 conditions that are true, okay? And the 4 conditions really revolve around if I took this beam that you see here on the screen, and I printed it out on a sheet of paper, and I folded it, and I folded it. Well, this one probably won't, but the next few will be, and you'll see what's going on with the next few. You're right though on this particular strategy, but future ones, you'll see what I'm talking about. If we look at this particular beam, this beam is symmetric with respect to 4 conditions. Okay, first off, it's symmetric with respect to geometry and its boundary conditions. We have a simple support on either end. So if I look at the reactions, I'm going to have a vertical reaction at A and a vertical reaction at D. And those are going to be the same conditions. The horizontal reaction isn't going to matter, because if it's symmetric with respect to loading, then the horizontal reactions are going to be 0. And that's the second point. It has to be symmetric with respect to loading. It also has to be symmetric with its stiffness. You can't have a different EI value on one half of the beam than you do the other. And finally, you have to be symmetric with respect to the point of interest. So for this particular beam, before the old way, I'd have to do 4 integrals. I propose exploiting symmetry. We only have to do 2 integrals. And the best part, if you look at the actual functions that we have to integrate, there's no foiling. Because if I'm only using the functions on the left, they're just 4x and x over 2. So all I'm going to do is integrate 2x squared from 0 to 10, and then integrate it again from 10 to 22. So it's a lot less than what was going on here with, I had the 176 minus 4x and the 22 minus x over 2. There is a lot less going on mathematically with this. This is a lot easier to deal with than the last one. Before I move on to the next tip, does this make sense? And as Mr. Enoch said, he said that this tip probably wouldn't be helpful on the homework problems. He's right. The 2 homework problems that you had, you couldn't exploit symmetry. So I admit that this tip by itself probably wouldn't help. The next 3 combined together, they will, guaranteed. But are there any questions about this? Because I really don't want to rush this. This is really important stuff. I'm going to give you a sec. Okay. And again, don't hesitate to stop me if you got any questions. Now, this next one has to do with the coordinate systems. So I want to talk about this problem. So let's, for sake of discussion, maybe just ignore all of this. This doesn't exist right now. This is, ignore that. Just ignore that. Okay. What you have here on the left is a cantilevered beam with a uniformly distributed load. This was a problem that we did. This was our very first beam deflection problem. And I gave you this problem and I said, what's the deflection at the free end? And when we did this problem in class, I think we got something like 0.911 inches or something like that, right? Now, here's the question, okay? So see how I've got the beam oriented? I've got the fixed support on the right end, and I've got a 15-foot long beam with 2.5 kips per foot, 2.5 kips per foot. Now, let me undo my erase. Now, let's take a look at the beam on the right. Now, can anybody just tell me, like, visually, what's the difference between these beams? Like, what did I do from the image on the left to the image on the right? What did I do, like, in terms of the image? I flipped them, and what Mr. Riggs and what Mr. Enoch's saying are exactly correct. I took the beam and I flipped it. Now, what I did here was a visual transformation. Now, what I want to do is I want to ask about the physics. Help me out. Is there really anything different between these 2 problems from a physics standpoint? In other words, I have a cantilevered beam that's 15 foot long that has 2.5 kips per foot on it. Does it really matter which way I look at it? No, it doesn't. Okay. Now, I'm going to do something here on the board here, and I want to show you what's going on the next slide, because there's a lot going on the next slide, but there's a very, very clear point to be made. Now, what we did in class was we had the beam with the fixed end right here, and we had, the load on it, and that was the origin. So this is the y-axis, this is the x-axis, okay? And what we did is we said, okay, we're going to cut a section and look at this this component over here. So we did that, and we said, okay, this distance is x, this is 2.5x, this is x over 2, and then we've got, this moment function, and we ended up getting moment was minus 1.25 x squared, okay? Did everybody remember us doing that in class? And I know I just sort of like threw this on here, but is everybody with me right now? Is everybody okay with this? Okay. Now what I want to do is I want to look at, well, what happens if I have it like this? What if I have the beam flipped, where I have, the support over here, so this is the origin. This is the origin. I got the origin here, but instead of putting the support on the right side, I put the support on the left side. So I cut a section and then look at this component. Well, I still have my, my distributed load, and I'm still wanting to try and find that moment. But there's more going on here, because not only do I have the distributed load, but I've got this vertical reaction here and this reaction here. And so what ends up happening when you chug it out is, so you end up getting a moment function that's a lot more in depth. It ends up being something like, I think it's like negative 281.25 plus 37.5x minus 1.25x squared. The algebra ends up being a lot more intense, and the reason why the algebra is a lot more intense is because you have a 37.5 kip reaction and a 281.25 foot kip reaction that you have to deal with. Okay, you didn't have to deal with that over here because you defined the beam so that the origin was at the free end. There were no reactions over here. But when you define the origin at the fixed end and you cut a section, you got to deal with those reactions. See, if I go back to the slides, let me show you this. This is nuts. I always thought this was crazy. So here's the beams. Okay, now here on the left, I put the free end at the origin, and on the right, I put the fixed end at the origin. When you look what happens, okay? So up top, this is what we did in class, and this is what I just did here on the board. So you have a real moment function, and then you have a virtual moment function. Now, let's go back to the principle of virtual work, because there's going on here on this slide, and I really want to digest it. We have a real moment function, and we have a virtual moment function, okay? So we multiply little m times big M, and then we integrate. And this is what we did in class, okay? Now, here's the crazy part, okay? What happens if you define the origin at the fixed end? Well, look at this. You get a much more nuts real moment function right here. It's much more nuts because it's, because you got to handle those reactions. And you're also going to have a much more nuts virtual moment function because you're going to have reactions from the virtual moments as well. And so when you multiply that out, you got to FOIL it, and it is just absolutely bonkers. Okay, let's take a look at that versus take a look at this. Now, I don't know about you, but I think it's a whole lot easier to integrate the one on the top than it is the one on the bottom. That's just me. But here's the nuts part. When you integrate them, you get the same answer because the math doesn't care what direction that you look. Ultimately, what you're doing is you're applying an energy principle. The energy in that beam is the same regardless of which way you flip the axes. So you might have this redonkulously big function, but I guarantee you the integrals are exactly the same. Mr. Enoch.
So is that meaning that that's because the support is not included in the cut in the top example?
Exactly right.
Why it's different. So
exactly
can we,
right.
When we have problems like that, can we just flip them and then just say that it's now the cut isn't going to include the most complicated parts of the beam?
Yes. That's exactly right.
Awesome.
That's what I'm saying. And I've got more to that. There's more to say there beyond just that one factoid. There's more to say. And the additional observations that can be made have to do with your coordinate systems. But right off the bat, I want to see if this part makes sense. And hopefully, I see the comment from Mr. Garrison. Hopefully, what you're seeing here can help simplify the homework that you did. What I want at the end of this lecture is for you to almost like, you don't have to physically go back and do the homework, but I want you to think, okay, if I had to do the homework again, what would I do differently? And you're going to have a little bit more of a complete picture here in a little bit. Before I move on, is everybody okay with defining the origin at the free end? If you define the origin at the free end, as Mr. Enoch said, and he put it beautifully, you're going to have just less stuff at the free end. You're not going to have reactions at the free end. You can ignore those reactions by defining the origin at the free end as opposed to the fixed end. Is it okay with this? I'm going to give everybody a second on this because this is important. Exactly right. That's the best way of saying it. Like, if I have a beam standing here in my office that's a 15-foot long beam that has 2.5 kips per foot, I can look at it like this, or I can walk around and look at it on the other side. I didn't change the beam. It's still the same beam. It's exactly right. Let me move on to tip 3. Okay, so let's talk about tip 3. Okay, so tip 2 said that that if you define the origin at the free end, the results are going to be simpler to deal with. Okay, now here's the thing, and I kind of glossed over this in my analysis up here, and that's when you cut the section, which way do you look? Now, I want to be absolutely crystal clear. Physics doesn't care which way you look. You're going to get the same answer either way. But one way is easier. Okay? Whenever you cut a section, I propose that you always look towards the origin. Let me show you why. So here's the beam. Okay? I need to derive a moment function. I'm going to cut a section, and now I'm going to look towards the origin. So let's digest what's going on this slide. Let's take our time with it. Okay. I've got a beam. I cut a section and I look to the left. Okay, so the first thing I really want everybody to pay attention to, yes, you can define origin. You're absolutely right. And between tip 2 and tip 4, I think you're going to be better equipped to do just that. Just wait till tip 4. Tip 4, I think, is really got something special to it. All right. The first thing I want you to look at is this. Okay, and I want to make sure that everybody is comfortable with these, the way I've defined this. The beam is 15 foot long. Okay, so if I cut a section here, this distance right here, that's X. But if that's X, this is 15 minus X. Okay, that's important. Okay, that's really important, because if you see that, what's going to happen on the next slide is going to look like a hot mess, and that is why. Okay, that and the reactions, but bear with me. Okay, so if I cut a section and I look to the left, I get this. So let's digest this. So I cut a section, I look to the left, I have a distributed load of 2.5 foot, and the segment is like X long. And so, you know, when you cut a section, you got an unknown shear and an unknown moment. Let's look at the moment. So I sum moments at the cut, and what do I have going on? Well, I only have 2 moments. I've got M going clockwise or counterclockwise, and I've got the moment from the distributed load, right? And I skipped a little bit. Usually I collapse that into a single point load, but I said, we've done this enough times, I think you can follow what I'm doing. The force is 2.5 times X, and then the moment arm is X over 2. So when I sum all that out, I get moment is negative 1.25 X squared. Now, before I flip on over to the next slide, everybody okay with this? Okay. The next slide I'm going to tell you is a hot mess, so bear with me. Now here's what happens when you look away from the origin. So now what I'm going to do is I'm going to cut a section and I'm going to look away from the origin. Okay. Now there's 2 points I want to make before we assess the hot mess. Okay. I'm going to go through the hot mess, but I want to make these 2 points before we start digging into it. The first point I want to make is this right here. That's the answer. Okay. Again, physics doesn't care which way that you look. You will get the same answer, barring you do the math appropriately. Okay. You will get the same answer, but there is an easier way. Hopefully I've made my case just by what's on the slide, you know, looking toward the origin versus looking away from the origin. I mean, you know, come on. But now let's go through it. Okay. So we're cutting a section, looking to the right. Look at that distance. It's not X. It's 15 minus X. Okay. So when we write out our, you know, moment expression, you know, when we start trying to fill in this table, let's try and fill it in. So let's sum the moments at the cut. What do I have? I've got the M going clockwise. All right. I've got the 281.25 going clockwise. Now let's look at that 37.5. It's not 37.5 times X. It's 37.5 times the quantity 15 minus X. Okay. So that's why I have this, you know, written like that. It's 37.5 times the quantity 15 minus X. Now, what in the heck is going on with that? Like, what is that monstrosity? Well, look at my distributed load, okay? Remember, how do you determine a moment? Force times the moment arm. What is the force? The force is the distributed load, 2.5 kips per foot, times the distance over which it's applied. And the distance over which it's applied is 15 minus X, all right? So that's how you're getting this part right here. So 2.5 times 15 minus X, that's the force. What about the moment arm? How far is it from the cut to the center of that load? Well, the cut to the center of that load is half the distance, half of 15 minus X over 2. So that's the moment arm, okay? Now, watch this. So here's the thing. If you look on the left, you should see we got some foiling we got to do because, you know, we've got 15 minus x times the quantity 15 minus x. So let's follow along. First off, what do we got here on the left? So here's the left. We got the m. We've got 2.5 divided by 2, so that's 1.25, and then 15 minus x times 15 minus x. You don't just square each term. You got to FOIL that out. And then the 281.25, and then on the right, how do I get from this to this? It's just distributing that out. The 37.5 times the 15, the 37.5 times the x. Okay. Now you keep going. How do I get from? Let's see. Let's use another color. How do I get from this to that? Foiling. First times first, outside terms, inside terms last, right? And then I take that 1.25, multiply it out. How do I get from the third line to the fourth line? I add up all the like terms. Notice when I look at this last equation, though, notice when I get here, look at this. I got this and this. There's a negative 37.5x on either side of the equation, cancel. There's a positive 562.5 on either side of the equation, cancel. And so all I'm left with is m plus 1.25x squared equals 0, and there you go. Again, I get the exact same answer that I did here, but I don't know about you, but I had a far easier time looking toward the origin than I did looking away from the origin. Moving on. So listen, my job is to I want to make it easier for you. Okay, that's really what I'm trying to do. The point I'm making. Oh God, I love my job. All right. My third tip is to always look towards the origin. The math will be easier. Okay, when you cut a section, you're going to get the same function regardless of which way that you look. Okay, some strategies are more advantageous than others. So before I go on to my last and final tip, I think tip 2 and tip 3 can kind of be combined. If you define the origin at the place where there's less going on, and then you cut a section and you look towards that origin, you're going to have less terms, you're going to have less math, and the math is going to be easier every time, and it will always result in a lot less algebra. Are there any questions about this? All right, let's talk about some system parameters. Just kidding. Let's talk about tip number 4. And before I talk about tip number 4, I want to show you something real quick because I don't want to just throw this out here. I want this to be really clear. And I think the easiest way to show you is to kind of just draw it out here with you. So, all right. As Mr. Enoch pointed, you know, if you have a beam that, let's say I give you a problem and it looks like this. Okay, so it's a cantilevered beam and it's a uniformly distributed load. Okay, now hopefully by now we agree that defining the origin at the free end makes the most sense. Okay, now there's 2 ways of doing this. One way of doing it is to actually just take the entire image and flip it and say, no, we're going to be dealing with this. Put the fixed in right here, do that, do that, do that, and then put my coordinate system right there. Okay, that's one way of doing it, and there's nothing wrong with that. okay? Another way of doing it is to instead say, no, 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 I'm not doing that. Why don't I just put my coordinate system like that? I mean, how is that any different, right? Just flip the coordinate system. I could flip the image and keep the coordinate system like I normally draw it, or I could just flip that, okay? That is a perfectly reasonable way of doing it. In fact, that's probably how I would do it because I don't want to draw the beam. I'm lazy. I'm just going to redraw the coordinate system. Okay, is everybody okay with this? That I can just take the coordinate system and just flip it? Okay. All right. Now, before I pull up the slide, I want to make a point about something. I want to talk about a definite integral. What's our goal here? Our goal here is to determine the deflection. Okay, so how do you determine the deflection? You're ultimately going to have a moment function, you know, a big M and a little m, and you're going to do some integration. Okay, so let's talk about an integral. Okay, this is structural analysis, and we're always going to be integrating polynomials. So it's always going to be something like, I don't know, 2x to the third minus 7x squared plus 4 over 3x minus 12. I've made that up. Okay, let's say this is an integral that you have to do. Okay, now I want to talk about the bounds to this integral. So let's talk about an integral from, let's say, 3 to 10. So I'll draw that a little bigger so that it's easy to see. I kind of did that a little sloppily. So let's say this is 3, and let's say that's 10. Okay, so we're evaluating from 3 to 10. Okay, now we don't have to do the problem. I just want to think about how we would do it. Okay, so follow this, logic, follow this in your head. Okay, so I integrate this. So what am I going to get? I'm going to get like a term that's x to the fourth, a term that's x to the third, a term that's x squared, a term that has x in it. So the whole thing, when it's integrated, is going to have terms that have x in it. That's going to have a variable in it. And then how do I evaluate the integral? I plug in the top number, I get some stuff. I plug in the bottom number, I get some stuff, and I take the difference of those two. Everybody with me? Now, if you're with me, let me ask you a question. Explain to me why the integral gets infinitely easier when I do that, when I make the bottom limit 0. Why does the integral get easier? Like, it's still the same integral. I'm plugging in the top number minus plugging the bottom number, but why did it get easier here? Because it's one less term. Because what you do, you plug in the top number into your answer minus you plug in the bottom number, but the bottom number is 0, so everything ends up being 0 on that lower bound limit. The entire thing on the lower bound is 0. Okay, and everybody in chat is saying the same thing. Now let's go back to the example. Let's talk about tip number 4. Okay, so here's what I'm getting at. Okay, hopefully after this lecture, you agree that we can orient the coordinate system whichever way we want. We can do the coordinate system like we have the y1 and the x1, or we could do the y2 and the x2. It doesn't matter. We can do whichever one we want. And we can place the origin wherever we want. My question for you is, why don't we use 2 coordinate systems? And I'm sure some of you are like, oh, come on, Dr. Mike, why the heck would you do that? Why would you use 2 coordinate systems? Why would you only use 1? Why don't you just keep it simple? Okay, here's why. Let's take a look at this particular beam. And I drew this beam a specific way. It doesn't really matter what's going on in terms of the load. Well, I don't blame you. I don't know that I like it either. But the point I'm making is that it doesn't matter what the load is. So that's why I have it sort of drawn as a wavy function. I'm going to have to do at least 2 integrals because I'm going to have a reaction here and I'm going to have a reaction here. So at a minimum, I'm going to have at least two integrals. It doesn't matter what's on top of the beam. I'm going to have at least two. I propose that defining a second coordinate system is going to greatly simplify the computations, and here's why. Okay, let me use my trick that I did before of crossing out, this lower image. Let me cross out all this and cross out this. Okay, I propose that if all we're doing is looking at the image on the top, and let's say we just use one coordinate system. Now, here's the thing. It doesn't matter whether or not we put that single coordinate system at the free end on the right or the pin support on the left. The end result is going to be the same. I'm going to have one integral that's like from 0 to 30, and then another integral that's from 30 to 46. If I flipped it, I'd have one integral that's like from 0 to 16, and then another integral from 16 to 46. But the point is, the point's going to be the same. I'm still going to have two integrals, and one of those integrals is going to have a non-zero lower bound. But here's the thing. Okay, let's go back to the concept. When we're determining deflections, all we're doing is summing up the energy that's stored by the beam. It doesn't matter if we integrate all of the beam using one coordinate system or a little bit of one coordinate system and a little bit of another. As long as our integration spans the entire beam, we're good. So I propose that let's look at the image on the bottom. So what do I have here on the bottom? What if I have two coordinate systems? I have one on the left and one on the right. And what I'll do is I'll take the one on the left and I'll integrate from 0 to 30. And then the one on the right, I'll integrate from 0 to 16. Like, I really want you to digest what's going on here. Okay, this is really important. Okay, because what we've done is two things. Number one, we have fully encompassed the energy in the entire beam. Like if that first integral goes from 0 to 30 and the second integral goes from 0 to 16, that's the entire beam. Like we've spanned the entire beam. But look at the integrals. Both of the integrals have a 0 lower bound. And so when we chug it out, we plug in the top number minus plug in the bottom number, but that bottom number is 0. So that whole term goes to 0. Makes the math so much easier. And because you're defining the function at the free end, as opposed to using that origin on the other side, the actual functions themselves become easier to deal with. So if you use these 4 tips, the problems just get so much easier, so much less to deal with. All right, I want to pause here for see if there's any questions. Exactly right. We'll do so what we'll do, 2 cuts. So what we'll have is we'll have like one cut here, and we'll look this way, and then we'll have one cut here looking that way. And so we'll have a set of functions defined with respect to x1, and then another set of functions with respect to x. And then you, exactly right. So look at your integrals. I'm integrating this first one, with respect to x1, and then the second one with respect to x2. And I just sum it up. Exactly right. Because here's the thing. You're not combining the functions. As Mr. Roman said, you're combining the integrals. Because ultimately, what are you doing? You're integrating to sum up the energy. So those integrals, all those integrals are is just a sum of all the energy that's being stored by the beam. So there's nothing wrong with just adding integral 1 to integral 2 because you're just adding the energy. Does that make sense? This is a really good discussion. As that's best way of putting it. Smarter, not harder. Exactly right. there is no point I'm glad that you're doing that. I'm glad that you're doing that. The one other point I would mention before we close everything out is there is probably I don't want to say a fifth tip, but I don't want you to forget what we discussed on Wednesday, and that's if you have a linear moment diagram, it's a line. You don't need to cut sections to determine the equation of a line. If it's a line, just use point slope formula. That doesn't really have anything to do with this, but it's still important it goes along with what Mr. Riggs said, smarter, not harder. I could probably entertain like maybe one more question or so. There you go. Yeah, and I mean, I in no way, shape, or form am suggesting that you don't do that. You like, look, it's 2020. You're engineers. I have no problem if you break out a TI-89 or a TI Inspire or whatever the HP or Casio equivalents are that can do algebra and calculus on their own. I have no problem with that. The only thing I would mention is the FE exam is not too far away. So keep in mind your Casio can do definite integrals. Okay, so if you don't want to chug out all the integrals, you can do those in your Casio. However, the smaller the integrals, like you could, going back to what I had said here, right? You could do integral on the top. You could integrate this in your Casio, or you could integrate that in your Casio, and you'll get the same answer. So defining the origin at the free end will make what you plug into the Casio all the more easy. I'm going to tell my TA not to grade this until Monday, so if you all want to give it another shot and do it over the weekend, you can. If not, you're good too. The Casio FX115 ES Plus is a very awesome calculator. All right, it's 10:52, guys. I'm probably going to have to call it so that I know some of you have class afterwards. Hopefully this was clear. One final thing. I created a short little video going through the example that we did on Wednesday, following these tips. It's short. It's only a few minutes long, but maybe it'll clarify some of what we're talking about here that matches an example that we did in class. So between that, hopefully all this stuff is a little easier. Monday, start talking about frames. You all have a wonderful weekend. I will see you all on Monday.